Welcome. My name is Andreas Quirrenbach. I'm at the University of Heidelberg, and in this talk I will discuss the radial velocity method and put it into the context of extrasolar system science. The radial velocity technique is one of the most important methods to find extrasolar planets and also to characterize them, that is, to measure some of their properties. To start off, I would like to give you a few numbers that are really easy to remember and that will help you to do estimates of the precision that you need to measure different types of extrasolar systems. So, the first set of numbers that are really easy to remember is the ratio of the radii of the Sun, Jupiter, and the Earth, which is about 100 to 10 to 1. The second set of numbers that is equally easy to remember is the ratio of their densities, which is about 1 to 1 to 3. That means the rocky Earth is about 3 times as dense as the gaseous Sun and the gaseous Jupiter. From these numbers, you can immediately also derive the mass ratios, because the mass is proportional to the cube of the radius and to the density. So the mass ratio is 300,000 to 300 to 1. The next number that is very useful is the orbital velocity of the Earth around the Sun, which is 30 kilometers per second. And the scaling of the orbital velocity with the semi-major axis of the orbit is velocity is proportional to 1 of the square root of a. Finally, the parsec is defined as the distance under which one astronomical unit appears under an angle of 1 arcsecond. Turning this around means at a distance of 1 parsec, 1 astronomical unit corresponds to 1 arcsecond. So with all these numbers that you can easily remember, you can do quick calculations very easily. For instance, if you take a system that consists of a G star at 10 parsec and an Earth that is a planet with a mass of 1 Earth mass at a separation of 1 astronomical unit in orbit around this star, the radial velocity of the star is just 30 kilometers per second divided by the mass ratio, which is 300,000, which is 10 centimeters per second. Equally, if you put the star at 10 parsecs, 1 astronomical unit corresponds to a tenth of an arcsecond, and you divide that by 300,000 and you get the astrometric signature, which is 0.3 microarcseconds. So with these numbers, it is really easy to do quick calculations of radial velocities and of astrometric signatures for different planetary systems. So with this in mind, I would like to go back in time a little bit and talk about expectations for extrasolar planets before the first were actually known. So one could have the naive expectation that other planetary systems are more or less the same as ours, which means you have small inner planets, larger outer planets. The typical orbital radii are a few astronomical units. The orbits are close to one common plane, so the mutual inclinations are relatively small, and the orbits would have small eccentricities. In this picture, which was generally the feeling of most astronomers around, say, 1990 or in the early 90s, with these expectations, it is clear that Jupiter is the easiest planet to detect. The radial velocity accuracy that one needs is of the order of 10 meters per second, or the astrometric accuracy for a Jupiter at about 10 parsecs would be ½ milliarcsecond, and the orbital period 10 years. So early programs aimed at the discovery of extrasolar planetary systems were long-term projects, typically with durations of many years, trying to find planets either astrometrically or with a radial velocity method. A few such systems were actually published. This is a famous example, Barnard star, one of the closest stars to the Earth, and also a system that has a very light host star, an M-dwarf. So the signatures are larger than for a sun-like star. Peter van der Kamp thought he had discovered 2 planets in orbit around this star. Unfortunately, he was mistaken. As we know today, Barnard star actually does have a planet, but it's very different from those that Peter van der Kamp thought he had found. So the actual planet that exists around this star has a mass of only 3 Earth masses, and you need a lot of modern radial velocity data points to actually securely discover this planet. So here is a plot that shows data point from the majority of the high precision radial velocity instruments around the world. But that is now several decades later. As I said, in the early 90s, it was expected that the first planets that you would find would look more or less like Jupiter, and you might have to be lucky to find one of these. The situation changed drastically in 1995 with this paper by Michel Mayor and Didier Queloz, in which they published a planet around the star 51 Pegasi. And the amazing fact is that this is a planet that has a mass that is close to a Jupiter mass, but it has an orbital period that is only 4 days. So this was totally unexpected, and it started really seriously the field of extrasolar planets. This was recognized by the Nobel Prize in Physics, as you probably all know, in 2019, that went to the 2 discoverers of 51 Pegasi b. So there were some real surprises from the radial velocity surveys in the mid-90s. First one I already mentioned, there are hot Jupiters. So there are types of planets that don't exist in the solar system. The second surprise was that many of the planets with longer orbital periods actually have highly eccentric orbits. So that points to a different dynamical history of the planetary system than the solar system. With the discovery of the hot Jupiters, it also became clear that it is easier to find at least some extrasolar planets than had been thought before. Also, it became very quickly clear that the diversity of planetary systems is larger than what had been thought before. And with the discovery of systems that are different from our solar system, it became also clear that we can learn something about the origin of the solar system by comparing it to these other systems. The whole field of how planetary systems begin and how they evolve got reinvigorated by the discovery of extrasolar planetary systems. So now you had a context that was much richer than just the solar system alone. So the first years of extrasolar planet science were really a period of collecting information about orbits, measuring masses, doing demographics, finding these different classes of planets. And soon the radial velocity method was joined by other methods that would also yield extrasolar planets. That's the transit method, the microlensing method, direct imaging, and today there are a few others. And one could start to draw diagrams like this, which shows the semi-major axis on the x-axis and the mass in Jupiter masses on the y-axis. And one could start looking at things like where are planets in this type of diagram, what types exist. So I already mentioned these hot Jupiters that are very far to the left in this diagram. There are also planets now that are at orbital radii that are much larger. So those are more similar to Jupiter in our solar system. One has to keep in mind that all these systems have severe biases in that they contain planets that we can discover, and they don't contain planets that are just beyond our detection limits. So here, the dashed lines give limits for a certain radial velocity precision, and it took some work actually to push down radial velocity precision in this range below about 3 meters per second. This diagram shows the historical development starting around 1995 and extending in the past few years, showing that the published planets discovered with the radial velocity methods started having tens of meters per second amplitudes. Then the precision went down to roughly 1 meter per second. And that's about where we are today. And there are many talks in this series that discuss issues like, for example, activity of stars that are really difficult to overcome. So pushing further down to this green line at the bottom, which is the radial velocity of the Earth, or one should say the radial velocity of the Sun due to the presence of the Earth, pushing down to that limit really is a challenge that is left for the future. But what happened over the past 30 years is that now we have a lot of different detection methods, some of them very fruitful, others still under development. So these can be grouped and classified into different classes. So on the left side here, we see dynamical methods. These are methods such as the radial velocity method that look at the signature of the planetary system in the motion of the parent star. These are methods that are in principle able to give you the mass of the planet because the signature on the star is proportional to the mass of the planet. There are other techniques that give you different types of information that can look at different types of systems. There's the microlensing technique, and there are photometric techniques. And among the photometric techniques, there's the direct imaging that works well for young planets far from their parent stars, so at large orbital radii where they can be separated more easily from the bright glare of the parent star. And there's the transit method that has been very fruitful, especially with space missions. So it is important to keep in mind that these different methods are complementary to each other in many ways. One type of complementarity is that they can be applied to different systems. They all have their intrinsic biases. Some of them are more sensitive to planets that are very close to their parent star. Amongst these, the transit method, the radial velocity technique. Others are more sensitive in principle to planets that have large orbital radii, such as astrometry. The other complementarity in this diagram is the type of information that you can get. Transit spectroscopy and spectroscopy of directly imaged planets can give you information about the atmosphere. Dynamical methods give you information about the mass. Microlensing also can address the mass ratio between the planet and the star. So it is worthwhile to develop all the methods in such a diagram and to see how they can fit together and how you can get different types of information from application of different methods. So as I mentioned, the radial velocity method is a dynamical technique, so it can give you mass measurements. But as you are well aware, what you get from a radial velocity is not the mass of a planet, but it's the quantity mass times the sine of the inclination angle of the orbit, m sine I. It's not the same. But one should take note that the expectation value of sine I is pi divided by 4, or 0.79. And the probability for randomly aligned orbit, random orbit orientation in space, the probability that the sine I is larger than 0.5 is √3 divided by 2, or 0.87. So in other words, the typical planet has a mass of about 1.27 times m sine I. If you can measure m sine I, it's not that much less than the typical mass that the planet would have. Also, only about 13% of the planets have masses that are larger than 2m sine I. So if you want to classify a planet, is this a terrestrial planet? Is this a gas giant planet? Some rough classification like that, m sine I is pretty good. Also, for statistical purposes, you can relatively easily correct or take into account into your statistical analysis that you are measuring m sine I. And for this type of observation, the radial velocity observation that gives m sine I, putting that into statistics is just fine. One should also note that for a transiting planet, the inclination is very close to 90 degrees. So m sine I is almost the same as m. And in many cases, you can even measure the inclination from the transit light curve precisely. So for all practical purposes, for a transiting planet, the radial velocity method does give you the mass. And then the radius is also known from analysis of the transit light curve, and mass and radius together give you the density, and the density is a very important clue for the bulk composition. So here is a very important application of the radial velocity technique. If you apply it to transiting planets, you get information on the composition of the planet. I should also talk about the complementarity of the radial velocity technique and astrometry. The Gaia mission is currently doing an astrometric survey of the whole sky, and when the final data from Gaia will be released, we will get information about planets orbiting nearby stars from their astrometric signature as measured with Gaia. So it is important here also to understand how radial velocities and astrometric information are complementary to each other. The radial velocity method, as discussed, measures m sine I. Astrometry measures two components of the orbit. So there are two components on the sky, one in the right ascension direction, one in the declination direction. And that is enough information to give you the inclination and the mass. So here you don't have the sine I ambiguity. That's a bit better than what you get from the radial velocity method. Also, if you have a multiple system, the radial velocity method carries no information on the mutual inclination of the system, whereas if you have astrometric orbits, you get this information about the mutual inclination. So in that sense, astrometry is better. They are really complementary in the sense that radial velocity is best for close-in planets, as the Keplerian velocity goes like 1 divided by the square root of a. The astrometric signal is proportional to a, so it is best for large planet orbits. The radial velocity method is somewhat restricted in its application to cool stars because only cool stars have a sufficient number of spectral lines, and only cool stars rotate slowly enough to have sharp lines for the radial velocity method. In contrast, astrometry in principle works for all types of stars. There's also a sensitivity to activity, which will be discussed in many presentations in this series for the radial velocity method. It is worth noting that astrometry is also sensitive to that, but less so, by roughly a factor of 10 maybe. There is a distinction between the two methods in that radial velocity method, the signal is independent of the distance of the star. It is easier to measure radial velocities for nearby stars because they are brighter. So the signal to noise ratio in the spectrum with a given exposure time is higher, but the signal is the radial velocity, which is the same no matter what the distance is. This is to be contrasted with astrometry, where the signal is proportional to 1 divided by distance. So the radial velocity method works out to relatively large distances compared to astrometry. Astrometry is really good for very nearby stars, but then because of this 1 divided by d dependence of the signal, it's really difficult to use astrometry to get good orbits of stars that are further away than just a few tenths of parsec. Whereas the radial velocity method, depending on the brightness of the star, works out to typically maybe hundreds of parsecs. If you have a bigger telescope, you can even push it to a larger distance if you want. Another important difference is that the radial velocity method works well from the ground. We have a lot of very good instruments on ground-based telescopes, whereas astrometry is really best done from space. So it is much more expensive to do it. It is clear from this list that there is a complementarity in that there's not a single thing that can be done by both methods equally well, or if you can combine radial velocities and astrometry from Gaia, you will have more than any one of these two methods will give you individually. So I already mentioned that if you can put together information from the radial velocity technique and from transit, you get information on the density. Or you can draw a diagram such as this, which is quite schematic. There are much more elaborate versions of this, but this shows the principle very nicely. You can plot the mass from the radial velocity technique on the x-axis, the radius from the transit technique on the y-axis, and then compare the position of a planet in this diagram with models for the composition of the star. So here we can see the planets in the solar system are the black stars on the bottom left. You have the terrestrial planets in the middle. You have the ice giants, Uranus and Neptune. On the top right, you have Saturn and Jupiter. And now we have many examples of extrasolar planets that we can actually place in such a diagram and see whether the planets consist of rocky material, of water ice, or maybe whether they are gaseous. So this is our first window into the structure of extrasolar planets. One can look at more complicated things, such as, for instance, the question, can a planet keep an atmosphere? So here's a diagram in which on the x-axis, we plot the escape velocity from the planet or solar system body. And on the y-axis, we plot the amount of radiation it receives from the parent star. And there's a light green line going from the bottom left to the top right, that is a rough dividing line between objects on the left or top left that have too much irradiation and too low an escape velocity so that they will lose their atmospheres. On the right and bottom, in contrast, these planets have a high escape velocity and they don't receive as much flux or not enough flux from their parent star to blow away the atmosphere. So such diagrams are very interesting to make because this is, of course, a necessary step to understand planetary structure, also to think about questions like which planets could retain an atmosphere and be habitable. So having the examples from our solar system is great, but also now being able to place extrasolar planets on such a diagram and look at the question whether or not they can retain an atmosphere is a very interesting scientific question that requires, of course, having a mass and a radius because that is necessary to calculate the escape velocity. Another interesting question is how precise are the masses that we can measure? So here's a study that looked at this question, and the color diagram are a few specific examples that you can find if you look up this paper that I quoted here. And we can see that in many cases, actually, we have masses, but the uncertainty is pretty large. There are, on the other hand, also quite a few for which the precision is better than about 20%. And of course, it's easier for a higher mass. And that is very important as an input if you want to analyze planetary atmospheres. You can do that with techniques like transit spectroscopy, in which you obtain a spectrum of the planet. But then in this figure, this shows an analysis of such transit spectra with different assumptions on how well you know the mass of the planet. So these are two examples for two different planets and simulations of observations with transit spectroscopy. And the bottom curve is always a probability distribution. If you have no idea what the, or no direct measurement of what the mass is of the planet, and going to the top, you have more precise information about the mass. And you can see, especially in the lower example, that even deriving relatively fundamental properties like what is the metallicity of that atmosphere of that planet, if you have a good spectrum, if you don't know the mass, you have a very large uncertainty, and you may actually misjudge what it is, because the mass, having a constraint on the mass, is a very important input parameter for such analyses. So this shows that the radial velocity method or astrometry, methods that can determine the mass of a planet, are very important in the context of future missions such as the James Webb Space Telescope or Ariel, that will do analyses of planetary atmospheres. These need input from the radial velocity method to find the masses that then can go into a joint analysis with these spectra. So this view graph shows what is required. We have to be able to measure the masses of a fair number of planets with a precision that in many cases goes down into the 1 or a few meters per second range, and that covers magnitudes that are rather faint for this type of technique. If you draw a similar diagram and do not use the V magnitude, but a red magnitude in the red part of the visible, such as an I magnitude or even a near-infrared magnitude, then it looks a little bit more friendly. So that means, because many of these stars are really cool. So measuring these radial velocities as input parameters for spectroscopy is a task for the future that is most easily actually done with spectrographs that work in the red or near infrared. But of course, there's more that you can get out of the radial velocity than just the mass of the planet. It's also orbital parameters. And one of the orbital parameters that you can hardly get by transits, for instance, is the eccentricity. We have lots of orbits now for transiting planets because these space missions, Kepler and TESS, are very effective at finding many transiting planets. But for most of them, we have very poor, if any, measurement of the eccentricity. In contrast, the radial velocity technique, the fit that you do to the radial velocity curve, always gives you the eccentricity. And the eccentricity contains very interesting information about the dynamical history of the system. A high eccentricity might be indicative, for instance, of a close encounter that may have ejected one planet and left the other in a high eccentricity orbit sometime during the evolution of the system. Planets that have short periods are also expected to have more or less circular orbits because tidal effects lead to a circularization of the orbit. So there's quite a bit of information that you can get out of eccentricities. So that is another important aspect of why the radial velocity method is important. Then there are multiple systems. So here I took one example, which is a system that has two quote-unquote planets. These are orbits for two objects that have about 20 Jupiter masses. So one might also call them brown dwarfs, but they are in a resonance system. So these are two objects that certainly formed like planets in a circumstellar disk. Otherwise, it is very hard to understand why they should be in a resonance system. Resonance means that, first of all, they have a period ratio that is very close to an integer, 6:1, or a ratio of small integers. One of them happens to be 1 in this case. And it also means that they are in a specific state in which there are variables that oscillate and don't circulate. For such systems, it is also important to get good measurements of the orbital parameters. So the 6 subplots here on the right, in the center and on the right, are these variables that show that this is a resonance system. This is really like a pendulum that swings back and forth and doesn't turn around. But also, I would like to draw your attention on the subplot on the left in the middle, which is the eccentricity evolution of the system. So these are numerical calculations in which the orbit on the previous view graph, the orbits of the two planets that had been fitted on the previous view graph, were integrated for a few 10,000 years in a numerical integrator. And they show that the eccentricities vary. They also vary with a period of a few thousand years. And so the eccentricities are very important input variables in the dynamical analysis of such systems. So this is another very interesting and rich subfield of extrasolar planet science that looks at the orbits in multiple systems. How do they evolve? Is there chaos or regularity? There are configurations like strong resonances that are also different from the solar system. So in addition to learning about the composition of planets, for which You can combine radial velocities and transits, or learning about planetary atmospheres. Learning about the evolution of orbits is also a very interesting subfield of extrasolar planet science, for which radial velocities are very important. So with that, I would like to come to the end and summarize a few of the most important points. So first of all, the field of exoplanet research really started seriously with radial velocities. Anything we knew before for planets around main sequence stars really was spurious. Radial velocities, radial velocity technique was the first method that successfully found planets around main sequence stars. Furthermore, radial velocities are important for planet statistics. Today, we know more planets from transits than from radial velocity technique, but there are very few transiting systems with periods that are larger than about 1 year, because the transit method has a very, very strong bias to shorter orbital periods. So here, radial velocities currently are really our best source of information. If you ask for statistics of planets with periods of 1 year or a few years, radial velocities are at the moment really the most important game in town. And the Gaia mission will change that in a few years, when we will also have interesting statistics from astrometry. I also mentioned that M sin I is really a good proxy for M in population studies. If you are not interested necessarily in the details of a planet, but if you are interested in a whole population of planets and statistical properties, it's really relatively straightforward to convert on a statistical basis your typical M sin I values into M values. Then the point, transits and radial velocities give densities. So that is a first glimpse into the physics of extrasolar planets. The most important thing perhaps about the physics, the bulk composition. Is the planet rocky? If it is rocky, is it more like a silicate composition or an iron composition? Is it maybe an icy planet? Does it have a big gas envelope? That can be answered by the combination of transits and radial velocities. Furthermore, having the mass of a planet is an important parameter if you want to understand a planet in more detail. If you want to analyze the atmosphere, if you want to understand whether a planet may be habitable, you better know the mass of the planet. And therefore, looking into the future, when habitability of planets will become an important scientific topic with advanced space missions, complementary methods that can give you the mass will remain very important. Then the eccentricity and being able to observe multiple systems gives you information about the dynamics. And the dynamics of extrasolar planetary systems is an important subfield and a very interesting subfield, because it tells you about how planetary systems form, how they evolve, about their histories. And finally, also radial velocities and astrometry from Gaia are complementary to each other. They can both be used to get masses, but they are applicable to different systems, and there are systems for which you can get the mass by radial velocity, but not by Gaia, and conversely. So the different extrasolar system characterization techniques are really complementary to each other. Radial velocities are important, and they will remain important in the context of other methods for detailed investigations of planetary systems to understanding their physical properties, and to do characterization. And with that, I would like to close this talk and thank you for your attention.